Hi, everybody. It's Dr. Jabo. This is the video for the asynchronous class. This video is optional. It's here to help you work through some of the problems from the Module 8 in class problem set if you're struggling with them. First, note that number 1 and 2, we already did those in class on Monday, and that number 5 was done for the videos that you watched as part 2 of the Module 8 video set. And then we're going to save number 8 to be done in class on Monday. So really our focus for this one class day is to just get through these 4 problems, which are numbers 3, 4, 6, and 7. And I'm going to work through in this video the 2 hardest of those, which is numbers 3 and 7. And then I think that you'll have enough tools to work through 4 and 6 yourself. If you feel comfortable working through 3, 4, 6, and 7 entirely yourself, that's okay. And then you don't need this video. So in this video, I am going to be working through numbers 3 and 7. All right, so let's just dive straight in. I will go ahead and navigate over to number 3. Both of these problems are actually really cool applications of the magnetic force as it's applied to, in this first example, either semiconductors or later in number 7 to mass spectrometers. So this Hall effect, one of the cool things that we'll see is that we can actually tell the sign of the charge carriers, which might seem like a strange thing to be excited about, because so far in this class, we've always just talked about electrons as being our charge carriers that are mobile. But it turns out that in the real world and modern physics, we have semiconductors where sometimes instead of the electrons physically moving, it's actually the vacancy of the electron that hops through that electron cloud that's free. And those are what we call the holes, the flow of positive charge carriers, this vacancy bounces. And so we use the Hall effect in order to determine that. So let's go ahead and see what the Hall effect is. So first of all, we have a piece of semiconducting material. It's a uniform magnetic field. Remember, B into the page, that's these X's that mean into the page. And then what we have first is just these, basic questions. Number 1, what is the current through the material? So this just comes from our plus and our minus. We know that current flows from positive to minus. So we have the current through the material is going to be traveling to the right. So to the right. And then that's just the conventional current direction. And then it says, assume the current is caused by the motion of positive charges. So we basically can say, what if it is holes, positive charges that are moving? What would we expect? And then if that's what we observe, we know we have positive charges. If that isn't what we observe, then we would actually have our electrons flow. So assume the current is caused by the motion of positive charges. What's the direction of the velocity of these positive charges, right? So remember that current is in the direction of positive charge flow. So that means that our positive charges are also moving to the right. And this is again through the material that we're looking for. In this case now, right, we can start applying our F equals QV cross B. So we can go ahead and say positive charges accumulate on one side of the sample and negative charges on the other. Which side of the sample is at a higher or lower voltage? So let's back up because I forgot to answer the main question, which is what's the direction of the magnetic force on these positive charges? So remember that we have that the F equals QV cross B. That's our magnetic force, and that's what we're looking for. So our velocity is to the right. Our magnetic field is into the page. And so what I'm going to do is take my right hand and I'm going to orient it so that it's pointed to the right. I'm going to push my palm down because I want to have the magnetic field coming out of my palm so that I can go V cross B. And I can then see that my thumb is pointing away from me, which in this case is towards the top of my piece of paper. So I have that my force is up. The force is towards the top, right? And so what that means then is if we look at what's happening, here's my sample, what's happening because my force is up, then all my positive charges end up at the top, kind of leaving an absence of charges at the bottom. So I've effectively created, right, from the motion of all of these positive charges in my current kind of going up with this net magnetic force, I've then created a separation of charge, which creates my voltage difference. So as we remember, a higher voltage is our positive, right? So the top is a higher voltage. So if I were to measure this voltage difference, and I knew that I put one lead at the top and one lead at the bottom, I could see if I get the voltage that's indicative of positive charge flow or negative charge flow. And so if we go then to this next question and we say, okay, let's say now that instead of talking about these vacancies hopping so that I have positive charge flow, let's go back to what we've usually done, which is the negative charge flow. So the motion of electrons. So my electrons, if my current is to the right, then my electrons are actually going to go opposite the current, right? So that's going to be the force on the electrons. So the electrons move opposite of my conventional current as defined by like the power supply long and short line. And so I still am going to do my magnetic force is equal to QV cross B. But because it's an electron, then I need to flip my result. And so I'm going to then have over here, if we look to see what happens, I have my velocity is now to the left. My magnetic field is still into the page, right? And so I take my right hand roll, and I point it so my fingers go now to my left. I am going to orient my palm so that it faces down because magnetic field's still down. So I can go V cross B. So V cross B, again, as if there's an arrow on my fingers, V cross B. Thumb is now pointed towards me. So that would be the force if a positive charge was flowing that way, but it's a negative charge. So I flip it. And so then I have to do that. I have to flip. And I get that it is also V cross B flipped away up towards the top of the page. So F sub B is still up. So go ahead and pause the video for a sec. Make sure that you understand the first time a positive charge V cross B went to the top of my paper that I'm writing on. I didn't have to flip it. Negative charge heads in the opposite direction. V cross B went towards me, except I flip it. So now it's still going. It was still going towards the top of the page. So F sub B is up, which means that if it was electrons coming in to this material, my electrons now move to the top, and I end up with my net negative charge at the top, positive charge remaining at the bottom, and then at the top is now a lower potential. And so the higher potential would be at the bottom now. So basically, I could tell by the sign of my voltage difference from top to bottom whether or not I have holes or electrons, which is very useful. And like I said, kind of explained down here in this blurb. And so we actually can figure out what the majority charge carriers are. And that depends on what we call the doping of the semiconductors, types of charge carriers that exist in the weird complicated band structures, and also the temperature of the material, because as you heat things up, you're kind of freeing more electrons, and so electrons tend to dominate at the higher temperatures. And so the Hall effect there is a direct result of simply applying a current, putting a magnetic field on it, and then seeing if the thing that you're applying the current through, so let's say that it was this wire, right? My pen is the wire, seeing if one top of the pen becomes a net voltage compared to the bottom, what the sign of that voltage is tells me the charge carriers that exist, positive or negative. So very simple, straightforward application of this Lorentz force law. Okay, let's move on to number 7. So number 4, you're going to work through yourself. Just a couple tips. You're going to just, in this case, right, we have the very kind of simple conservation of energy that you just start with, you know, U initial plus K initial equals U final plus K final. U still equals QV. So this is all the stuff that we had talked about. That was on our module. I guess that probably showed up in module 4 when we first talked about potential. And so in this case, we're actually creating our velocity, right? So we're kind of just accelerating here some charges plus 2e, notice the plus 2e, and they're accelerated from rest. So they all sort of started over here with some rest, and then they're going to be exiting, and we make a tiny little hole here so that then they come out with some V final. So you're going to find this V final when they leave, given that they've been accelerated at that V final. That V final then becomes the initial V for what's going to happen here, where we're then going to send them through this velocity selector. So this part here, where we're going to be able to, you know, say that we want to have the magnetic field so the particles emerge undeflected. I want you to go ahead and refer back to C number 2 from class that we had done in order to remember what we talked about with that velocity selector. Okay, so that'll help you with 4. Number 5, as I said, was done in the video modules part 2. Was worked out, so the circular motion. And number 6 is a pretty straightforward application of those circular motion type problems. So I'm actually going to do the more challenging one in this video, where we look at a mass spectrometer, which is a direct example of the circular motion of charged particles in a magnetic field, and their radius is going to depend on their properties. So by figuring out where they hit along, say, a screen, if all the particles are doing this, where they hit along that screen tells me about their properties. And so that's the fundamental idea of a mass spectrometer. In addition to this video, there are hints on the following page to kind of help you navigate it. Really, the circular motion part's not the hard part. The main part that people kind of mess up is with figuring out the mass of these isotopes. Okay, so we have uranium-235 and uranium-238, and we're going to separate them using a mass spectrometer. It's uranium hexafluoride, so UF6, 6 fluoride, 1 uranium, and it's accelerated through 15 kilovolts, and the atomic mass of fluorine is 19, and so then it gives us the atomic mass of uranium-235 and it also will later, for the 238, it'll tell us it'll be 238 instead of 235. We don't need to be told that. I guess we just know that, right? So U238, from just what we know about chemistry, it's going to be 238 AMU. Okay. So the first question is, what's the velocity of the ionized molecules with U238? And then we'll find the velocity for the U235. And then they're going to go into, with that velocity, our magnetic field, and then have a arc that depends on that velocity. So basically what we need is to find the mass of the uranium-238, because for the velocity, as you're hopefully comfortable with by now, is simply going to be our conservation of energy, right? We're going to say here that our delta U is equal to our change in our delta K, which is the same way of me saying, right, I'm going to take my QV times, or in this case, it would be the Q delta V that it's given. Q delta V is going to be equal to 1/2 mV final squared. So I'm just doing the same old conservation of energy. I'm given Q because they're all going to be singly ionized. That says so here. And I know the delta V, I know the Q, I want V final, so I need the mass. So that's where we're at. So we want to find the mass of 238. I'm going to first find it in AMU. So I'm going to be saying that it's 238 EMU, but what I really need is UF6. So I want 238 plus 6 times 19 AMU. So that's really the only hard part about finding that total mass. And then we know that 1 AMU is equal to 1.67 times 10 to the minus 27th kilograms. And so I get the mass of the UF6 238, for lack of a better notation, is going to be equal to, let me see, I've already calculated that, 5.88 times 10 to the minus 25 kilograms. So that's one of the things that we're going to just put on hold. And then I'm going to use that up in this top equation. I can solve that top equation for my V final. I see my V final is equal to 2Q delta V over M all to the 1/2. And so what that allows me to do then is solve for my V, and I'm going to just label this V238. And again, the subscripts are all just there for me to use however I need to, so that I can keep track of what I solve for, so that it makes sense to me. So this lets me know this is the speed of the 238 upon entering my magnetic field. Magnetic fields don't change my speed, so that's my speed in my circular motion. So I'm going to just plug that in, and again, it's singly ionized, so I'm just using the charge on one electron, and I get 9.04 times 10 to the 4th meters per second. So pretty fast, as we'd expect. I'm going to go ahead and highlight that because I know I'm going to use it when I get to the magnetic field stuff. All right, same thing when I'm going to do the mass of U235, and specifically that's again UF6. So this case would be 235 plus 6 still times 19. That's my AMUs. And so then when I convert that to kilograms, I get this 5.83. So very close. So I'm keeping my sig figs here. Minus 10 times 10 to the minus 25 kilograms. And I'll point out that difference in maths in a second, because we're going to come back to it. It's actually really fascinating. And then over here, I can then say my V of my 235 is going to be calculating all of these values. And again, keeping appropriate numbers of sig figs, it's going to be slightly faster in this case, times 10 to the 4th meters per second. Does it make sense to you that it's faster? It should, because it's lighter by 3 AMU. And so therefore it's going to have more speed because it has the same kinetic energy, the same Q delta V. And so therefore more speed for less mass when we have that same kinetic energy. All right, awesome. So those are my two different speeds. And then what I am going to point out here is that my change in mass, the difference in mass, is only on the order of 10 to the minus 27th. So 5 times 10 to the minus 27th kilograms. So that's tiny, like crazy tiny little mass that is different between these. And what we're going to see is that they are separatable easily. Like the scale of what we get is going to be something that we could like just physically make very easily to separate them by their radii. So a tiny mass difference makes a big difference when we're talking about their radii in these magnetic fields as we go to our next step. Okay, so there was really nothing new there, but that's usually where people get stuck on that problem because it's just the nuances of finding the mass and making sure that you're carrying enough of your sig figs over for those velocities. So now let's move on to the actual new stuff, which is the mass spectrometer uses a magnetic field of 0.5 Tesla directed out of the page, right? And so we're going to basically have here, these again out of the page, is these dots. So that means that the B is out of the page. That's kind of how we illustrate that. Here's going to be over on the left, the input into that. So this was going to be the V that we found for each one entering that field. So let's all here, right, see what what we're expecting. So the speeds, they come up, right? And they're gonna basically make our half of our circular motion, not the best circle, but before they collide. So I'm gonna have here, I'm gonna draw them in two separate colors, and one of them that's going a little bit faster is gonna go further. And so what we want to actually then see, right, as we work through this, the B is the out of the page, and it's the same for both. So we have to look at our circular motion. So remember, for circular motion, our force is always perpendicular to our velocity, right? F equals QV cross B. In this case, my V is perpendicular to B, so this just equals QVB sine of 90. You know, I like the sine of 90 for my cross products. And so my force, right, my magnitude of my force is just going to be equal to QVB. That's my net force. That's my only force. So what I do is I say that QVB equals my centripetal acceleration, which is my mv squared, my centripetal acceleration times my mass, ma, mv squared over my r. And the r is actually what we want to find, because what they've traveled, where they're going to hit, is twice that, the diameter of these circles. So over here, d is equal to 2 times r. So now this is my fundamental circular motion equation, which you've seen in the videos, you'll be navigating yourself. We can see, right, that R is going to be equal to mv squared over qvb. So one of those v's cancel. So mv over qb. The Q, again, singly ionized, right? And all of these are essentially just magnitudes. And so we can then solve for our various diameters. I'm going to just throw in the 2 to start. So I'll say D is equal to 2R. And so I can solve for my D235, and I can solve for D238. And I can do that by plugging in the mass that I've already found. I can solve the velocity I've already found, Q singly ionized, and then the magnetic field is the 0.5 Tesla that I've been given. So, and when I do that, then what I get is this. I get the D, and again, enough sig figs to make this problem work. That's the other stopping point for some people, is it all looks the same, but you're just not carrying enough digits. So D235 is 1.321 meters, and D238 is 1.327 meters. So you're like, well, these are basically the same. What are we doing here? But what that means is that this distance between them is actually going to be equal to 6 millimeters. So delta D is equal to 6 millimeters, which in the big scheme of things is actually really reasonable, right? Like that's a super manageable amount. If I needed to make a little slit that my, 235s were going to come through and another one that my 238s were going to come through, and I needed to like machine that and then have them go into different places, I could totally do that. 6 millimeters is actually quite large in the terms of like manageability, right? And also it's 6 millimeters, it's on the order of like 10 to the minus 3 of our normal things. It's a macroscopic visible amount. We can all see 6 millimeters easily. And that was caused, to remember, this was caused by a delta M on the order of 10 to the minus 27th kilograms. So like this tiny, 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 tiny mass separation creates this very measurable quantity of the distance. And so that, is really why we love this example. It's kind of this really cool application that allows us to actually very carefully measure things like mass. And the mass spectrometer is this really, kind of simple setup where then you can see where something hits. And that allows you to know its mass very accurately because we can measure positions pretty well, certainly on the scale of what they're talking about with these delta M's. So that's that. Okay. Like I said, this video is totally optional. I feel like we're in a really good spot with magnetism, but you guys just need to be practicing your right hand rules and your circular motion stuff, your cross products, and getting in the mindset of the magnetism. And then we will be continuing this on Monday. Okay. I hope everybody feels good about the exam. Reach out with any questions. I just didn't want to kind of force us to be in class, after such a long week when I know that you've been putting your all into being prepared for this exam. I appreciate that you did that. So good job, everybody, and take care.